Right then, I think we're ready to start up things then. So, hi everyone. My name is Ricardo Lopez. I'm a third-year PhD student here at the University of Michigan. And for those of you that weren't here for one of the earlier weeks where I talked about gamma ray imaging, I'll just reiterate again that my particular research area has to deal with radiation imaging methods, which happens to be the talk for today's lecture. So I'm pretty excited to get started on this and everything. So real quick regarding questions, feel free to bring any questions that you have up in the Q&A. And then at the very end, I'd be happy to answer any of the ones that come up. Otherwise, one of the moderators may be able to answer your question as the presentation goes on. But if there's any at the end, I'd be happy to talk about it in more detail if anyone wants to. Cool. So to begin, before I go into the general topic of imaging, I wanted to start off by just talking about what some of our motivations for using these kinds of systems or these techniques. So there's a wide array of applications for imaging systems, but the two that I like to focus on, at least for today's lecture, happen to deal with, of course, nuclear safeguards or nuclear security. One option here on the column on the left would be for search and emergency response scenarios. So currently there's a lot of deployed systems that would typically just measure like the relative count rates or the dose rates in a particular area, and they could be used to help localize a source in the case where you want to locate one or one's gone missing in, say, like a warehouse, for example, and you have to pinpoint and locate it in a timely manner. So that's one option. However, with this kind of a method, it's these kinds of systems are fairly sensitive to the background and any kind of subsequent background fluctuations that you may end up having in that particular type of environment. So depending on where you happen to be at or where what kind of a system you're using, it may be difficult to end up using. However, imaging systems, don't have this kind of sensitivity to background, and they can also give you this more direct or directional information regarding the source of radiation. And we'll definitely get into a lot more detail about that. The other application would be for nuclear verification scenarios. Here, the premise is that you have inspectors that are attempting to monitor or verify the location or composition of source in, say, a drum, for example. And the scenarios where you often see this being employed is, say, for treaty verifications, more specifically, say, for warhead verifications between nations. And under these circumstances, inspectors typically would want to deploy passive systems and in order to monitor the source. And depending on where you happen to be deployed or where you're doing these kinds of measurements, there's a lot of other constraints that you may have to keep in mind. But also you want to also make sure that the inspectors themselves or that the users themselves are both comfortable with using the system and that it's actually fairly easy to use. So something that's fairly small and compact that has a very small footprint would be ideal. And also a low power device that doesn't, place a significant burden on, say, the facility, if it's always going to be placed there, or something that, that is low power enough that someone could, just carry around with them if it just requires, say, a small portable battery to power. Over on the right image is an example of several years ago, the University of Michigan developed the dual particle imager, which is actually the predecessor of my current project. But as you can may note from that image, it's essentially made up of these giant racks with several PMTs and associated scintillators. And as you can probably imagine by looking at the picture, though it might be hard because it's kind of hard to get a sense of scale right there. But if you're familiar with the type of equipment that's pictured there, you can imagine this is definitely not something that's very mobile and not something that, someone would be very easily be able to move and transport given the amount of PMTs that are being used. So, well, this is an example of definitely a type of imaging system that definitely works. it may not be, ideal under all circumstances, for example. So the main two imaging methods I'll be talking about or discussing in detail today are going to be pertaining to both neutron imaging and gamma ray imaging. So for the introduction to neutron imaging, I'm going to introduce the topic of neutron scatter cameras and how they work. So pictured here over on the left schematic is a situation where, say, you have two separate detectors. So you have two separate volumes, and you have some neutron emitting radiation source off to the left. Now, if you have a neutron that's emitted from this particular source and then elastically scatters off one of the detectors, and then before exiting is able to scatter off the second detector volume, then you get a lot of important information under these circumstances. Now, the detectors that are pictured here are just general, and the actual detector material could be one of many, but for the purposes of this demonstration, let's just say it's an organic simulator. So when you have an elastic scatter off one of these detectors, you'll have the case where you'll have photons emitted from the events. And from each particular scatter, you'll get some kind of information from the detector. Of course, you'll know the energy deposited in that particular event, since you know how much light corresponds to that particular interaction or how much light you captured for that event. And you'll ideally know the location in X, Y, and Z. And finally, you'll get a timestamp so you know what time did this event occur in. Similarly, for the second scatter, the second elastic scatter in this example, you would get the same kind of information. Again, you'll know how much energy the neutron deposited in this event, its location, and the second timestamp for that second scatter. Now, with this kind of information, so you can imagine, since you know the time between events and since you know the locations, you know the distance, you can actually calculate the velocity of the neutron as it traveled from the first scatter to the second scatter. And based on the velocity, you can calculate how much energy that neutron had at that point in time, which we refer to over here onto the right as the ETOF, which stands for the energy at time of flight. So it's the energy that the neutron had during its flight path along that particular vector, if you will. Now, if you add this energy at time of flight plus the energy that was deposited in the first scatter event, then you have a rough idea of what the original energy for that neutron was as if it was emitted from the source. And then based on some kinematics, you're actually able to figure out, based on the ratio between the energy at time of flight over the total energy of that neutron, it corresponds to the incident angle of that particular neutron, which is pictured here over on the left, where you have this lever arm, which is the vector between the two scatter events. And then with respect to that, you have some angle theta, which is the scattering angle. And since we live in a three-dimensional world, this directional information isn't just, like a single vector pointing in one particular location in space. It's more so can be thought of as a kind of ring in space where you're fairly certain, based on the kinematics that your detector or that your imager recorded, that this source should lie, or that original neutron originated from somewhere along this cone in space. And as you collect more and more information, or you get more and more of these cones, they all should intersect at some location in space, which would end up corresponding to where your neutron source is situated at. Now, it's a very similar story for gamma imaging. In this case, with the Compton camera, you again have separate detectors or separate volumes where you have a gamma emitting source over to the left. You have a gamma ray that then Compton scatters in, say, one of your organic scintillators. And then subsequently, as it hits another detector, it would ideally get absorbed via photoelectric absorption. And one of the ways that you can achieve this is by having, say, your detector be inorganic scintillator, since you're more likely to have photoelectric interactions with that due to its higher Z. Now, again, in the first interaction, in this case with the gamma ray Compton scatter in the organic scintillator, we again have the same kind of information as we did before, where we know the energy deposition, the location, and the time. And likewise with the second interaction, in this case, the photoelectric absorption. However, this time though, you would be able to figure out what the initial energy of the gamma ray is if this particular sequence of events transpired. So if you have a gamma ray, constant scatter, and then get fully absorbed in your second volume, then obviously if you just sum the two energies, then you would get the initial gamma ray energy. And like before, based on the way that the kinematics work, you can essentially make a relationship between the energies and the incident angle. Unlike before, though, this expression's a lot less neat than before. Before, we just had the ratio of the energy time of flight over the total neutron energy. Here, it's a bit more complex, but the end scenario is still the same, where you have this relationship with the scattering, the incident angle of your particular particle, in this case, the gamma ray. And like before, you'll end up obtaining another cone in space where that gamma ray, chances are it originated from somewhere along that cone. And again, if you measure for long enough and you collect enough of these double interaction events, such that you get enough of these cones intersecting at some particular location in space, you can make a fairly good guess that that's where your gamma source is actually situated at. So some cool things to note, though, is that you can also gate on particular energy regions that would be of interest to you. So for example, if you are imaging a particular gamma source, say cesium-137, which has a fairly strong gamma emission at 662 keV, you can particularly gate, say, between 600 and 700 keV to specifically image these double interaction events that have a energy within that energy gate. And that would mean that even if you have several gamma sources out in the field of view, if one of them is cesium and the other ones, say, aren't, say, with something like sodium-22, where you would see something, say, at 511, then if you placed an energy gate and then created a gamma image using that information, you would be able to discriminate the cesium source and be able to just focus solely on that one. And again, this kind of method really only works if this specific sequence is followed. So first the constant scatter, and then a photoelectric absorption, such that you actually get the full energy deposition of your particular gamma ray in this case. And I'll also note that in order to have this actually work very well, you also have to make sure that your system itself and the associated electronics have a sufficient time resolution that you can actually sequence these events correctly and be able to tell which ones indeed came first. So time resolution will end up being a combination of making sure your electronics don't have are sufficiently good, and also that your detector material of choice, or your scintillator, for example, has a fast enough response. So once you have all these cones, what you can do is essentially sum them all, project them onto the surface of a surface around your system. In this case, say a sphere, and then you can add all these onto all these cones on top of one another, essentially, and what we'll be calling simple back projection. And that will allow you to ultimately end up converging in a particular location in polar space. The way that you end up reading this kind of image is essentially that the x-axis on the bottom represents your azimuthal angle, where 0 would be directly ahead of you, negative numbers would be towards your left, and positive azimuth angles would be over to your right. The y-axis is very similar. It would be your altitude angle, where 0 would be level, positive numbers would be up, and negative angles would be down with respect to the detector. Now, what you're actually seeing here in this little animation is demonstrating how, in this particular measurement, I placed a source directly ahead of the system. So I would expect the hotspot to be at coordinates of 0, 0. And we indeed see that as you acquire more and more of these cones, you do end up seeing that kind of behavior, though a very small number of cones, because you have very low statistics. You're not as confident ultimately in the final hotspot, if you will. And you can see that at those low cones numbers, the hotspot is rapidly changing back and forth across different angular locations, and that just has to do with the fact that you don't have the statistics really to make a sound conclusion at that point. But as you get more and more, you end up seeing that eventually you do end up with the hotspot occurring at a 0, in this particular case. Now I'll explain a bit on how the image in the previous slide was actually obtained, but just walking you through this simple back projection scheme. So I mentioned before that you essentially have your imager and you have these cones essentially, and what you want to do is be able to project it onto some kind of surface. What a lot of people like to use is just a sphere that's centered at 0, which that origin point could correspond to, say, for example, the detector or the imager that you're using. And then what you can do is essentially break down that sphere into a 2D matrix where your azimuthal angle would be your rows and your altitude angle would be along your columns. And once you think back to the information that you obtained back during the actual measurement, I mentioned before that you have your location, which under normal circumstances, you would record that in like X, Y, and Z coordinates or Cartesian coordinates. And what you can do is essentially just transpose those or transform them over to spherical coordinates so that you have a position on of a pixel on that spherical surface that I mentioned before that you can actually relate to back in Cartesian space. And the vector between the two interaction locations that I mentioned before, we'll refer to that as the lever arm. And what I'll essentially do is be able to give you a frame of reference with respect to your scattering angle or your angle of incidence, since an angle by itself doesn't tell you much unless you have some kind of vector right to, or two vectors rather, in between them so that you have some kind of frame of reference. And now the angle between that lever arm and any kind of given pixel on the sphere we'll call beta. And this is like the most complex or hardest part of this particular algorithm to really wrap your head around, because for each individual scatter event, what's really happening is that cone, if you will, is contributing a bit to every single pixel on that particular surface. It just so happens to that those that actually lie on the cone have a higher contribution than those that don't. So that's why we still have to perform this calculation on each individual pixel on that particular matrix. Finally, alpha is just related to the actual scattering angle that I talked to before. In this case, this would be for a neutron scatter camera, which is why you just have this simple relation of the energy at time of flight over energy. And then finally, the actual cone equation that's used for the projection is given by this expression here, which is very similar to Gaussian distribution, as you may be aware, where all the terms that I mentioned before end up making their way into here. And that's essentially how you're able to create these cones in polar space. And I know that this is very abstract or very mathematical, so help alleviate that kind of confusion, here's a couple of test cases that I basically just set up where I have very simple scenarios. In this case, say I just have two detectors, and let's say we have interaction happen or a scatter happen in detector 1, which corresponds to this X, Y, and Z coordinate, and we have a second scatter happen in location 2, which corresponds to this X, Y, and Z coordinate. And let's just say that based on the energy deposited, we end up getting a alpha value, which is equal to cosine squared of the theta of 0.5. And then finally, we just assume 10% uncertainty in all the factors, which we can then plug into the Gaussian expression as before. What does the cone end up looking like? This. So this alpha of 0.5 actually, if you do the math, corresponds to a theta value of 45 degrees, which is why these white dotted lines here that I included in the picture over to the right are at 45 degrees, which would mean that this cone corresponds with a scattering event that had an opening angle or angle of incidence of 45 degrees. And based on the way that the scatter happened relative to where the neutron presumably came from, it's centered at around 0. But that just has to do with the coordinates that I gave in this case. What's really important here is to note the fact that, yes, based on the numbers that I gave you, the opening angle in this case would be 45. Here's another case where now still a fairly simple setup, but now I just changed the relative position of the detectors, and then I changed the coordinates appropriately. Everything else is still the same. And again, we have a 45 degree opening angle for the interaction, but now the cone's over to the right, which would correspond to an azimuthal angle of positive 9 degrees. And you can kind of make this out over in the middle schematic here, showing where the neutron came from relative to the two detectors in this case. Now, this is all well and good, but since this is a polar image, things could get a bit weird, if you will, at certain in certain directions. And to better showcase this, here's an example of again, two detectors, except now they're stacked on top of one another. So this means that now, of course, the coordinates change appropriately, but then what does the resulting cone end up looking like under these circumstances in the matrices that I've shown before? Is just a line at 45 degrees in this case, based on the fact that it's essentially coming from above, and based on the way that the axes are set up, you don't get like a circular cone. It's a line just based on the coordinate system that we're using here for this particular image. So again, just something to note, things could get a bit weird, if you will, or not so intuitive at first glance if you look at single cones sometimes. Now, for next up, I want to talk about some of the effects that some of the parameters and how that ends up affecting the cones on a case-by-case basis. So here, using just some MCMP simulations, we simulated, just single double scatter events to see how if we change certain parameters, how does that end up affecting the final cone that you end up seeing. So if you look at the column on the left, everything is constant other than the relative uncertainty and, like, say, the deposited energies in this case. And we see that at low relative uncertainties, we have a fairly well-defined cone, fairly thin band at the highest intensities. That's all well and good. The white dot that you see at 0, 0 would correspond to where the source, quote unquote, truly is. And since we see that it lies along the path of the cone, everything's fine or working as intended, if you will. If you look down though, as you start to increase the relative uncertainty, the cone, as you can see, ends up getting thicker and thicker, where ultimately, if you go all the way down to 100% relative uncertainty, now it starts to really be rough to gauge, where exactly is the source. Usually you'd say it lies along the cone, but with such a thick cone, you essentially just have a circle in this polar space. And if you end up, say, adding 100 of these 100% relative uncertainty cones together, instead of having a very nice condense and small hotspot at 0, 0, what you'll probably end up getting is a very large, high intensity or high valued hotspot at 0, 0, but it would be very wide. So it would actually be pretty hard to ascertain whether the source is truly situated in that small angular region, since it can lie really anywhere within the thick or really red blob distribution, if you will. Over on the right is showing what happens when the scattering angle of your particular particle, how does that end up changing your cone? So you can see that with very small scattering angles, in this case starting at 25 degrees, we again have a pretty standard cone. But as you go to higher and higher scattering angles, you actually end up seeing that these cones end up getting a lot thinner and a lot bigger. Now, depending on your scenario and what you're actually measuring, may or may not this may or may not be a good thing. Generally speaking, though, having a lot of cones of very large scattering angles tends to, from what I have observed in practice, lead to very well condensed and very well defined hotspots. However, depending on the way you have your setup configured, large scattering angle events may not be very common or very easy to actually obtain. So you may not end up having a lot of these events, depending on, of course, your geometry. But again, that varies from system to system. But in general, very large scattering angle events end up getting thinner cones most of the time. Of course, there's also assuming that your relative uncertainties are fairly low, which could end up being really useful and to converge on a particular source. Proceed with the whole idea of simulations. I showed before what happens like on a case-by-case basis, but then I wanted to show what happens as a systematic response, or rather, when you have thousands of cones, what is the general behavior of changing these these parameters by a small amount? So in this case, we simulated the 36,000 of these double interaction events, and then changed some parameters to see how does the image end up getting affected. More specifically, the hotspot, or how does that change in terms of how well converge does it get in the azimuthal and altitude directions, which was represented with these full width F-max values. And the way these were attained is essentially you can take a slice along either the azimuth or altitude direction, and then fit a Gaussian to that distribution. And by taking the full width F-max of that, you can have a general rough idea of how well your convergence is. So what you want to see is really low degree values that would indicate that you have a very tight a very tight distribution, which will correspond to a very small, well-defined hotspot. So to begin with, if we have, say, 36,000 events where they range from 10 to 100% relative uncertainty, which would say, let's say there's a fairly normal scenario, and then you get a pretty well, very symmetric, fairly easy to tell where the source is in this particular case. Everything looks good. If you start chopping it down, though, to cutting down that range in half, where now your relative uncertainty is between 10 to 50, visually speaking, it still basically looks the same. If you look at the full width F-max values, they're not all that too different, really, from the first case. So even cutting the uncertainty range in half didn't really appear to have that big of an impact. But then if you cut it down even further and to about like a quarter, then if you look at the actual images, you can kind of see that, okay, it did kind of converge down a bit tighter. And that's also in agreement with the lower full width F-max values. But as you can probably tell, you really get very little payoff by having to restrict the uncertainty range by such a large amount, which is kind of surprising. It may not be something that intuitively you would think would be the case. It's a kind of a similar story with the scattering angle, where on the top right image, we have 36,000 events again, where this time the scattering angle was anywhere between 10 to 170 degrees. And we see, again, we have the same fairly standard image, but then once you start restricting the scattering angles to a narrower range with 10s to higher valued ones, then we end up seeing that almost right away, you end up seeing a pretty big improvement in the full width F-max values. And now you might think like, okay, cool, then why don't you always just set up your geometry of your imager, or set up the actual experimental setup to basically just focus on high scatter events? You could definitely do that. However, what you may end up having to deal with, though, is a very low count rate, if you will, of those particular events, which may mean you may end up needing to measure for a lot longer periods of time. If you were a lot more forgiving in terms of which scattering angles you would allow your imager to see, then you would get a lot more events, though granted, right, your image may not be as well defined. So it's trade-offs ultimately at the end of the day. It would be up to the user to determine how they want to optimize between measurement time and image quality, which ends up being a pretty big question sometimes, or a pretty big problem to work out. Cool. One last quick thing with regards to all this simulation work. I mentioned before that we had this lever arm that corresponds to the vector between the two interaction points. It should be noted that actually, if you create a scatter map of these lever arm distributions, they can actually tell you a lot about what you would expect the image generated from this kind of lever arm distribution to look like. So going back to like the quote unquote ideal or standard simple back projected image here over on the bottom right, on the top, it's the corresponding lever arm distribution that we obtained that would actually generate all the events that were used to generate that image were plotted on this scatter map for the lever arm distribution, and we have seen that kind of response. Now, in and of itself, that doesn't tell us much until we start doing some comparisons. So by changing the number of lever arms, which ultimately corresponds to changing or limiting the allowable scattering angles with your system, very clearly impacts the resulting image. If we go back to the very bottom here, that's going back to the quote unquote standard, well-symmetric, well-defined image. But as you lower and lower the number of lever arms, you start seeing very obvious artifacting in your image and this kind of distortion. That just has to do with the fact that you're restricting the allowable number of scattering angles, which ultimately ends up resulting in these kinds of imaging artifacts, which you wouldn't really see, or as much, it wouldn't really have that much of an impact though at a higher number. Not only is the number important, but the way that they're distributed is also important. So in this case, we have the same number of lever arms, if you will, and these scatter plot distributions, but the way that they're distributed relative to one another is different, and the resulting images clearly show that there was an effect with that. Where over on the left, it's fairly symmetric and fairly equal with respect to the theta, the azimuth and altitude directions, but we see a pretty significant change over on the right, which is that the altitude direction was severely degraded, and you get this kind of squish or elongation along that particular direction based on this distribution. And to better clarify this, here's an example of a very simple case where we just have these lever arms going along the z-axis. We are told that the source is placed at, say, z equals 0. And then as you pick any dot along this lever arm distribution, this essentially corresponds to the center of a particular cone. And since all of these come from that particular source, no matter where you happen to lie along that line, they need to end up intersecting this star or the location of the source. And as you can imagine, if all your cones only have the option of intersecting the source at that particular way, then if you were to take an image on this, it would be elongated along the azimuthal direction. Well, you would have really good, you have a really good hotspot in the altitude direction, sure, but you can see very clearly that it gets very distorted along the azimuth. So then the question would be, oh, well, where along the azimuthal direction is your source actually situated at? And that can cause some issues down the line. So that's it for a lot of this methodology discussion and discussing some of the techniques that are actually used in simple path projection in this case. What I'll continue on for the sector is actually talking about some actual experimental applications that are actually done in research. And what I'll mainly be using or referring to in this case would be some of my research work with the imager that I work with. So here at the University of Michigan, we've developed the handheld dual particle imager, or the HDPI. It's composed of a combination of organic scintillators, which are in the shape of these 6x6 by 50 millimeter bars, and some inorganic scintillators, which are these very small cerium bromide cylinders. So over on the middle is an actual picture of the active volume of the arrays. We sandwich everything in between two SciPM arrays, and that's how we actually collect the photons created during this installation process. And over on the right, top right, is a render in 3D of what the system actually looks like without having all the additional supports and the CPM arrays in the way. And on the bottom right is an example of how the 8x8 pixel CPM array is actually populated. So as you can imagine, an 8x8 CPM system has the capacity for up to 64 pixels on a particular side. Given the fact that we're using 12 bars and 8 cerium bromides in this particular geometry, though, you can kind of see that we're not actually populating the entire 64 pixel array. What we're doing, what I'm showing you here on the bottom right is a top-down view of like the actual layout, where these blue squares correspond to pixels that have a bar placed on them, while the red circles correspond to where we place the cerium bromide cylinders. And since it is a dual particle imager, it essentially serves as both a neutron scatter camera and a Compton imager in one, where neutron imaging is performed by having neutrons elastically scattered between any two of the organic simulated bars, while gamma imaging is achieved by having a gamma ray Compton scatter out one of the bars and then get absorbed in one of the cerium bromides, ideally. Now, here's a little video demonstrating that process. First, we'll have an incident gamma ray hit one of the bars and then be absorbed in one of the blue cerium bromides in this case. While shortly after, a neutron's going to come in, double scatter between two separate bars, and this is essentially demonstrating the whole cone process again, where this time, if we have several cones, right, or if you measure for long enough of them should intersect at some common location, which we would say this is where the source is situated at for that example. To give you an idea of how this HGTPI has actually performed, I'll briefly talk about a couple of experiments that I did at our lab with this system. Now, I did a gamma ray focused measurement and a neutron focused measurement where with the gamma ray one, I placed two different gamma ray sources out in the field of view of the imager at the same time. One of them is a cesium-137 source, while the other one's a cesium-22 source. And the goal for that measurement was to show that A, we can image both sources at the same time in the same field of view, and B, be able to discriminate one from the other, and to also see how long does it actually take us to make that discrimination between two gamma sources based on their energies. And with the neutron measurement, I wanted to, again, demonstrate that we'd be able to image multiple neutron sources out in the same field of view, while at the same time, I placed a cesium source, again, out in the field of view. And this would be to demonstrate that a gamma source won't accidentally be classified as a neutron source using the neutron imaging method. So we should only see two hotspots on the scenario over on the right, even though I had three sources out. So here's the results that we obtained based on the gamma ray experiment, where I placed, or rather, I used two different energy gates, one centered at 511 and the other one at 662, which corresponds to the emissions of the sodium and cesium sources, respectively. And what we were able to demonstrate was that, yes, not only can we image and differentiate between these two gamma sources in the same field of view, but we were able to do that within 18 seconds of starting the measurement, which is what these images are actually showing you. These are the imaging information or simple backwardated images that we obtained using the data collected within the first 18 seconds of the measurement. Now, of course, that was only the first 18 seconds. If you measure for, say, a bit longer, say a couple minutes, where you end up having a lot greater number of these gamma cones, then you actually get these much better defined hotspots. And this after we apply our converging algorithm to simple backward-projected images. And you see that we have very clear and distinct hotspots over centered to the location of the sodium source and location of the cesium source. And these black outlines that you may or may not be able to make out on the slides correspond to where the sources were actually placed at during the actual experiment. So we see pretty good agreement between those and the highest intensity locations of the hotspots that we ended up seeing. So that was great to see. It's a similar story with the neutron imaging results. So again, we were able to see hotspots corresponding to both the puberty source and the californium-252 source. Again, both of these are emitting neutrons, which is why you end up seeing two hotspots at their respective locations. But then over far to the right at 9 degrees azimuth, you see nothing, which is what we'd expect, because cesium-137 doesn't emit neutrons, so it wouldn't make much sense to also see a hotspot over there. But then this goes to show that, yes, based on the neutron imaging methodology, we are definitely able to discriminate between gamma ray sources in the same field of view, and also we're able to successfully measure neutron sources, multiple neutron sources at the same time. Now, these I'll go back real quick. So these images that you see here, these simple vector images, are great and are fine for, say, presentations like in this case, or for publications where you're essentially limited by default to this kind of 2D media where you have to represent or visualize this imaging information in 2D. Now the question is, what's next? How can we improve upon that? Say you have a working imaging system, how do you convey that imaging information to a user very clearly so that they can actually make the correct call in saying where the source should be is located at based on the data, but also ideally it should be able to convey this information clearly enough that even an untrained person would be able to, make use of the system and be able to correctly tell where the source is located at. And so to answer the first question of how can we convey this imaging information to users in some other media other than traditional 2D plots, there's a lot of answers to that particular question. One that I'll touch on, since it's the one that we decided to go with, was visualizing this imaging information in mixed reality or augmented reality, if you will, using a headset. And I'll talk a bit more detail about that in the next few slides. But also, another important question is, how can we obtain the source distance information with imaging? So with simple backwards directed imaging, or at least with the particular process that I demonstrated and talked about today, you are, I'll go back here, you are able to say with a fairly high degree of confidence that a source is located in, say, whatever, in this case, like -40 degrees azimuth and 0 degrees altitude. So all you can really say is the direction that the source is relative to the detector. What you can't necessarily say is how far away is the source. If I were to hide this, say, the Californium source behind a couple boxes, it would be able to correctly say that, the Californium's in the direction of those boxes, but it wouldn't be able to say, oh, it's the second box, along that direction. All it knows is it happens to come from that particular direction. It has currently no real idea of distance. And knowing that distance would be actually very powerful, especially for, say, search scenarios where you really want to locate that source as quick as possible. And so instead of using simple back projection, which is only one of the several kind of imaging techniques that are out there, you can use triangulation, or rather 3D imaging methods, in order to obtain that distance information. And again, I'll cover that a bit in the next couple slides. But to continue on with the mixed reality approach, how do you take this data that you got from the, say, in this case, the HTTPI, how do you convey that to a user in a very informative way? Well, what we were able to do last summer was essentially make use of the Microsoft HoloLens 2 device. It's this headset that's pictured over to the right, that using the sensors in the front is able to create a live spatial mesh of your current environment. So if you combine this spatial mesh with the directional information that you obtain from the imager, you would actually be able to overlay that together in order to get a pretty good sense in real time where the source could potentially be located at based on the imaging information. And to just very briefly go through the general process, you have the data that's collected by your detector and associated equipment. That data gets fed into a data acquisition computer that does all the, the calculations, that figures out what the angle is relative to the lever arm and performs essentially all the cone calculations. And then finally, it sends that information over to the HoloLens, which it could then use to project onto its spatial mesh environment. And one of the things that we were able to do was we were able to develop an application on this HoloLens device that uses the double interaction events to do this overlay on the spatial mesh. And since it's a dual particle imager, of course, the user has a lot of custom options available to them. The most noteworthy one being the fact that you can specifically set the HoloLens to, say, neutron mode or gamma mode, where you would be able to image either type of radiation source. And you can see that, oh, if you're getting a bunch of counts, but you're not seeing a hotspot, that would basically just mean you need to swap over to the other mode to actually see the correct particle type. And of course, there's a lot of other options available to the user, such as changing the color option in case the user is susceptible to one particular type of color blindness. They can enable or disable the visualization of the mesh, and they can also bring up the energy spectrum information, whether that be the gamma spectra or the extracted neutron emission spectra that the detector gets. And to demonstrate this, or before that, I basically glossed over this at a very high level, but if you're interested in more details about this particular application of using that imaging technique in combination with mixed reality, we have a paper available that you guys are free to take a look at on Scientific Reports. It's open access, so you shouldn't really need any permissions, or there shouldn't be any paywalls to access it. So feel free to take a look at this one in case this whole process in general is of interest to you. Otherwise, we have a little video demonstrating essentially the capabilities of everything that I just mentioned in the previous slide, where what you'll be seeing here is the detector collecting data on live time and projecting that imaging information onto the spatial mesh of the HoloLens to demonstrate to the user where the source is situated at based on the information collected. So one of the things that you may notice in this video is that you can kind of see that like black here, like this kind of black shadow around everything. That's actually the spatial mesh of the HoloLens. It's a weird quirk where if you take a recording on the HoloLens, it by default like puts this kind of black, if you will, on the mesh. I'm sure there's a way to disable it. It's not the most pretty thing in the world, but when the user is actually wearing it, that white filter is actually present. It's literally just the hotspot information that's actually viewable to the user. So it's a lot less cluttered when you're actually wearing the device. The spatial mesh is actually shown here in all these white triangles. That's one of the options. If that's a lot of too much visual information, the user can just disable that in order to make things a lot more clear in terms of the user's view. But again, here starting off right now, it's in neutron mode, so it's able to see the Californium source. But the user can bring up, using one of their hands, a little hand menu to swap over to the alternative imaging type. In that case, it would be the gamma mode, and you would still see that the hotspot is still in agreement with the previous one. In this case, since Californium emits both particle types, so no matter which one you're actually using, you'll end up getting a hotspot in the correct direction, or rather the location of the source. And I will note here also that this process has the same kind of limitation before as it doesn't know the distance. Based on the application, what it's doing is it's essentially just intersecting the first thing that happens to be in the spatial mesh according to the hotspot. So in this case, since there's nothing obstructing the source from the detector, it correctly actually ends up hitting the expected, the true location of the source. If, again, I were to place this Californium, say, inside a box, and then I placed another box in front of it, all this application would do is highlight, that initial first box. So you would have no idea actually that the source is actually in the box right behind it. So that could be one potential limitation for that case. However, if on the contrary, on the opposite hand, if you're like verifying, say, a source within a barrel or within a storage container, and it's the only thing that that happens to be within the near vicinity, and that's what actually ends up getting intersected with the hotspot or with this directional information, then you can be fairly confident that, okay, yeah, there's a source present and it happens to be within this barrel in this case. For this last little video, I'm just going to show how I can take the source, move it, and then the system is able to recognize that the source moved. Once the user basically just clears the previous hotspot information, it'll start acquiring, or it'll start deleting the old directional information from where the previous source location was. And as soon as that's cleared by the user, it'll start actually projecting the new hotspot location based on the new data. And since it's only been a couple seconds, it's not quite on the source, but you can see very quickly that the hotspot did shift far over to the left, near where the source was actually placed at. Of course, if we just waited a couple more seconds, we would end up getting the same kind of a nice hotspot as we did over to the right. And then finally, I talked about how you could potentially use 3D imaging to work around the whole not knowing the distance issue. Well, you can use multiple detectors, or say, in this case, say multiple HUDPIs at the same time, or use a single detector at different locations in time to basically get a measurement of a source in different positions in space. That would allow you to actually do like triangulation, or rather, you would construct these cones in this 3D space using voxels, where you voxelize your particular measurement or your particular environment. You would just voxelize it in small cubes, and you can intersect your cones with these cubes. Since you have the equation of your cone for your particular event, you can figure out which of these voxels ended up intersecting that particular cone, and that lets you build a cone of voxels, if you will, in that three-dimensional space. And if you have multiple cones from different locations that end up, coming from the source, they should end up intersecting where the source is located at in this 3D space, as shown here, like over on the bottom right. In ideal sense, this is how it'll work with. So one of the things that we've been working on this summer has been essentially improving or generating an algorithm that can basically take the data from the HTTPI, do these 3D algorithm calculations in voxelized space, such that we can get these kind of 3D voxel distributions that ultimately we will be able to represent using the HoloLens in a new application. And that's currently a work in progress, but to give you a sneak peek of how things are going, over on the left is an example of a measurement where I did with the HTTPIs, which is located here as this black outline. In position 1, position 2, we were measuring a Californium source placed here, and it's represented by this red sphere. And by rendering in this case, or rather only plotting the voxels that are like the highest top percentile of intensity values, we see that in 3D space, we do have a distribution of voxels clustered close to the source, would be indicative of it correctly actually finding the source and being within, a couple centimeters of where the source is actually situated at. So right now, that looks great, and we're working on further developing the algorithm to not only work on this scenario, but also work with multiple sources potentially, and then also heavily shielded sources, also something that's of interest. But at the same time, we're also working on getting this distribution over the lab ported over to Unity so that the HoloLens could actually start showing this in this mixed reality approach. And right now, that's been a current work in progress with us, where we're essentially messing with voxel transparencies, where voxels with very low values are very transparent, so that for all intents and purposes, the user can consider them unimportant, while voxels with very high intensities end up being a lot more opaque and would correspond or be more indicative of where the source would potentially be situated at. So right now we're hoping to have that worked out within the next couple months. But as you can probably tell from the presentation, radiation imaging in of itself is a very broad topic, and there's a lot of ongoing work in the field by several groups around the world in terms of developing or refining current imaging algorithms and the like. So I think for the purposes of this lecture, though, that essentially covers everything that I wanted to discuss. I'd be happy to answer any questions in case anyone has anything. I know that just about wrapped up before 2, so you're all free to go. So this is the end of the lecture, but of course, if anyone has questions, I'd be happy to stick around for a couple more minutes and answer anything.
Yeah, okay. So there was a question from Sophia Shuda referencing an equation you had on slide 4. Why does the equation for energy after scattering at some angle seem very, very similar to the equation for intensity after polarizing a light beam at some angle?
Let's see. Here, correct? Slide 4?
I believe so.
Right. I would assume it just has to do with the fact that, now I'll preface this by saying that I'm not too familiar, at least in my research, with regards to polarizing light and everything, but my guess would be has to do with the fact that the scatter is the energy position on the scatter is very much dependent on the angle of the scatter. So as you have smaller angles, right, you have less energy position as compared to large ones. I would assume that there's some kind of a relation with that. Unfortunately, I don't think I can give a very solid answer with that because I'm not too familiar with the topic, unfortunately. Okay, so I guess next we have one from Eric. When calculating total energy, why is the Compton camera more accurate? Well, it's not so much that it's more accurate, it's the fact that you can actually, if the particular sequence of events actually follows through where you have a Compton scatter, then a photoelectric absorption, just summing them is enough to actually get the total gamma ray energy, since the gamma was actually absorbed in that subsequent or second event. As opposed with the neutron scenario, and I'll go back here, where your best guess at the initial neutron energy is based on that time of flight calculation. And now the issue is that energy at time of flight calculation is pretty sensitive to A, the timing, and B, the position. So as you can imagine, if you're off in your position, because of how fast the neutrons are actually traveling, that significantly actually impacts on the energy that you end up calculating, because you may end up calculating it as it traveling a lot smaller or a lot farther. Well, a lot is relative in this case, it would be a couple of millimeters. So even being off on the distance by a bit could significantly impact, how much energy you think the neutron actually had in that particular case. It's a very similar thing with the time. If you're slightly off with your time, or if your timing resolution isn't really good, you can, based on the data, make the wrong assumption that, the neutron took either like a lot less or a lot longer than it actually did. And again, that would also subsequently impact your energy calculation. And since the initial energy is essentially very much dependent on your calculation for your energy time of flight, that's why it would you could say it's more uncertain, because the energy time of flight calculation is just based on the way that it's actually calculated. There's a lot more associated errors with it, which of course, if you improve your system, you could address it, but only to a certain amount. There's a reasonable limit in terms of how well you can actually get that error down under most normal circumstances, of course. Cool. All right. Otherwise, I have my email on the slides in case anyone else ever has any questions after this talk. Otherwise, I want to thank everyone for listening in for today, and hope to see you all for tomorrow, where this kind of imaging week, if you will continue, where Alexander is actually going to be talking about time-encoded imaging. So I hope you all look forward to that tomorrow.